Hello, this is Alan Roble again. This time I thought I'd do a short series of videos on HPCC architecture, that's high performance computing cluster, and how to work with it, how to leverage its power correctly. So HPCC, high performance computing cluster, the secret's in the word cluster. It means that really it's composed, one HPCC system is composed of one or more nodes, that's computers effectively in their own right, so, or nodes as they're called here. So in this example, you see I've got four machines or four nodes going to go to make up one 4 HPCC system. And the idea is to really take code to the data. So when you compile some ECL or some code, it's compiled into a library, a .so file. This .so file is then sent to each individual node, and then it's executed on that node locally on the data on that node. So the data itself, which can be petabytes, is sprayed or distributed as evenly as possible over the nodes. The example you see here is actually quite badly is an example of something that isn't distributed. You'd hope to get within a couple of percent usually. Obviously you don't only get intermediate results when running executing locally, but you generate intermediate results which are then, you can then aggregate the intermediate results to generate a final result. There's nothing to stop you running globally over the entire data set, the single logical file here, but if you're doing that, you're not really using HPCC to its power. And also when you do run globally, you're continually monitored for SKEW. That is that your work unit will crash if it finds that the data on one node is too different from the amount of data it's processing on another node, and it's the difference between the sizes. I think the default's about 10%, and then your work units will crash with SKEW error. So I better define, this is a badly distributed file, but I better define what SKEW is and what to avoid. So in here, SKEW is defined as a maximum of the absolute of the average part size minus the part size for every individual node divided by the average part size. So for example, for node 4, that's a size of 4, but the average size is 7, so the SKEW is going to be 42% if you do the calculation above. And this, in fact, node 3 is 42% again, but in a different direction. But because of the abs, obviously, you get the same sign. And the worst SKEW is 71% for node 1, generated by node 1. So the actual SKEW for this logical file is considered to be 71%, and it would well crash work unit with anything like that. As I said, I think the default it checks for before it crashes about 10% margin it gives you. So that's what SKEW is, and that's what you want to try and avoid. Now obviously when you run locally, you don't have, you'll never get SKEW problems. So that's one of the advantages of running locally, apart from the fact that everything is local on a particular machine. So that's the what a logical file looks like. Let's just see what it looks like in ECL. So you've sprayed in a file, and spraying in does what it says. It just sprays in unintelligently, knows nothing about the what you want, how it's to be distributed. As far as it's concerned, it's a fixed length, variable length, or whatever file, and it will make its best bet at trying to distribute evenly over all the nodes, but it's an unintelligent distribution. And you can see it if you look at a file in ECL Watch. For example, there's a file parts tab, so you open a file and one of the tabs to do with a file is its file parts, and you can see here I've got a sprayed in file, and it's not exactly the same. You don't expect it to be completely equivalent, but it's done a fairly good job of of distributing a single logical file over each computer there. So the actual command to distribute correctly, so once it's sprayed in, you yourself can read it, but then you can distribute it in the way that you know you want it to be distributed for any subsequent processing you'll be doing on it. So in my example here, I know that surname and first name is going to be quite a good hash to get an even distribution, and there's all sorts of different hash functions, hash 32, hash 64, hash CRC. You can look that all up in the reference manual. So just a silly example, you could hash by the number 1, and that would put absolutely the entire file on a single node, which is exactly not what to do. So that's about the daftest distribution I can think of. Just showing that. Let's Control Z out of that. There. Now let's getting back to the ECL watch or the SKEW. I think here we are. So when you're running Thor, it's monitoring what's going on, and so you don't really want to run globally, you want to run locally. And so as I've said here, the way to use Thor correctly is to just do all the heavy lifting on each individual computer, each individual node, generate intermediate results, which you can then use to generate a final result. So for example, if this file contained ages of people and I wanted to find the average age of all the people referenced in this single file, what I would do is I would sum the ages here. I would all on each individual node. I would then count the number of people on an individual node, get that intermediate result for all nodes, and then at the end take the intermediate results and sum the ages, sum of the sums, and then sum the counts, and then do the division globally. But that final trivial calculation at the end is nothing at all. All the work, 99.999% of the work, is done locally on each individual node. And if you do it run locally, you won't get SKEW errors. So I think in the next video, I'll demonstrate how to actually achieve this result. All the best. Cheers. Bye.